Hey everyone, welcome to another episode in Physics is Fun. Today is going to be about finding work done on a half-cylinder shape. Let's jump into reading the question. A mass M is pulled. That should say pulled. I'm not sure how I missed that. So pulled by a frictionless and massless string over a frictionless half-cylinder having radius r. A. Assume speed is constant and show that the force F equals m times g times cosine theta. B. Integrate work equals the integral of force dotted into dr and find work done if the mass moves constantly from the bottom to the top of the half cylinder. C. Now, if the half cylinder is flipped with the mass m equals 2.5 kilograms on the flat leftmost side, determine the work done on the mass by a force of F equals 16.0 newtons, pushing across the distance d equals 2.20 meters at angle theta equals 25 degrees above the horizontal. Also by the normal force and by gravity and by the net forces on the mass. Let's draw the picture for this problem. There is a half cylinder laying like this with the mass sitting about here at angle theta, a distance r away from the center. The mass is pulled by the string over the cylinder like this. Don't be tricked by the string. The force that applies to the mass will be tangential with the object it is sliding on. So in this case, about up and to the left. Well, with the picture drawn, let's move on to part A. Our speed is constant, so that means we have no acceleration, and thus is just 0. Let's make a free body diagram, so start with a base. We should find the axes we need first, so if we put x in direction of motion, or the direction of the force, the axis will be pointed left and tilted up like this. So dash out the starting axes on the base, and the mass obviously has weight, so straight down like always. Mark out the theta angle following the diagram above the horizontal. Since we made the x direction of motion, that's where the pulling force is, and since the mass touches, the cylinder will exert a normal force back. This will be in the y direction, perpendicular to the force. Dash out a small tail for x and y axes to apply the angle trick by going around the right angles. Starting at theta, going around down is 90 minus theta, and then that next angle is theta right here. This one will give us the x and y components we need. With the FBD, let's sum up the forces in both directions. So in the x is F minus m times g times cosine theta equals 0. And in the y, n minus m times g times sine theta equals 0. With the forces written, it's now time to calculate. Rewrite the F minus m times g times cosine theta equals 0. And add m times g times cosine theta to both sides. This gives us F equals m times g times cosine theta, which proves part A. So let's move on to part B, the fun integration. Rewrite the work equals integral of f dotted into dr. We have to think about the distance traveled, as this is not a straight path, so we cannot just plug in like usual for dr. With this being cylindrical or circular, we need to use polar coordinates to convert to the correct distance. Polar coordinates have a radius and an angle theta in a pair. For the right distance, we need to find the arc length, which of course we all remember to be arc length equals radius times an angle theta in radians. This means to find dr, we need to find the change in arc length in relation to theta, so dr equals r times d theta. With f and dr solved for, it's time to plug in and calculate. Rewrite work equals integral of f dotted into dr. Part B asks for the work from the bottom to top half of the cylinder, so from the ground, or 0 degrees, or 0 radians, to the top half, so perpendicular, which gives an angle of 90 degrees, or pi over 2 radians. This will be our bounds for our integration. So we get the integral from 0 to pi over 2 of m times g times cosine theta, dotted into r times d theta. we can pull all the constant coefficients out front, so m times g times r times the integral of 0 to pi over 2 of cosine theta dotted, or times d theta. Integrating cosine theta is just sine theta. So we have m times g times r times sine theta. That goes from theta of 0 to pi over 2. Plugging in gives m times g times r times sine of pi over 2 minus m times g times r times sine of 0. Sine of 0 is 0, so that term goes away, and sine of pi over 2 is 1, just leaving the left term of m times g times r. So the work done is m times g times r. With part B solved, let's move on with part C. Flipping the cylinder so that the mass rests on the flat surface, being pushed at this angle across the whole distance like this. Let's draw a new FBD for this one. This is using a regular axis with motion to the right. So the mass starts with a base and dash out the starting axes. The mass has weight straight down. The force on the mass is angled above the horizontal, just like this, and the force pushes in this direction. We can find the angle for the force to be here from using the opposite angle. And the cylinder exerts a normal force back on the mass, which is directly straight up in the y direction. I write the variables given with m equals 2.50 kilograms and d equals 2.20 meters and F equals 16.0 newtons, and theta equals 25 degrees. This is all that is needed, so it is now time to calculate. Rewrite the work formula. The work done on the force equals F times change in distance, or R, times cosine theta. Plugging in gives 16 newtons times 2.2 meters times cosine of 25 degrees. The work done on the force is 31.9 newton meters, or joules. Now for the work on the normal force equals F times change in distance, or R, times cosine theta, and plugging in normal force times 2.20 meters times cosine of 90 degrees. Since it is perpendicular, cosine of 90 degrees goes to 0, so there is absolutely no work done on the normal force. Finding the work for gravity equals F times change in distance, or R, times cosine theta, and plugging in again gives m times g times 2.2 meters times cosine of 90, which goes to 0. No work is done by gravity. Now finding the work done by the net forces, just simply add all of the work done of each force. So 31.9 joules plus 0 joules plus 0 joules. Work on the net forces equals a total 31.9 joules. After tackling an odd problem with an odd shape, we showed that F equals m times g times cosine theta, which helped us find the work, and also by using polar coordinates to find work equals m times g times r. With the mass on a flat surface, we easily found some more work done, which equaled a total of 31.9 joules. I hope these intro problems are as helpful for you as they are for me. Thank you so much for watching. Hope you come back to learn more exciting material, and see you next time.